Hello, everyone. My name is Jaehyung Kim. I'm a research engineer at CryptoLab. And today I want to talk about FHE ring packing, which I think is quite affordable and convenient in practical sense. So this will be kind of a trip to find out efficient ring packing method. And the final destination will be Hermes, which is the ring packing method we presented in this year's crypto. This is a joint work with Youngjin Bae, Jungin Chun, Jihan Park, and Damian Stelle. So let me start the presentation right away. So in this work, we first consider FHE ring packing problem, which is an adaptation of usual ring packing problem to FHE setting, which now have bootstrapping. And we suggest generic acceleration tools for FHE ring packing and observe what happens if we apply these acceleration tools to existing methods. We propose a new FHE ring packing method called Hermes, which solves some problems of existing methods. And this shows 40 times higher throughput compared to state-of-the-art ring packing method. And finally, we discuss a little bit about application to transciphering. So now I proceed to the definition of ring packing. So in fully homomorphic encryption, there are basically two categories of schemes. So one is LWE-based scheme, and the other is ring LWE-based schemes. And the name of the categories denote the default format of ciphertext they use. So as you all know, TFHE and FHEW are LWE-based schemes, and BGV, BFB, CKKS are ring LWE-based schemes. So LWE format ciphertext and ring LWE format ciphertext have its own advantages over the others. So for LWE format, the advantage is high granularity and fast latency, meaning that it is good at dealing with small number and individual ciphertexts, individual messages. And ring LWE format is good at scalability and high throughput, meaning that it could be preferable when we are dealing with massive number of data. In addition, LWE-based schemes are good at computing individual beats, while ring LWE-based schemes are good at elementary operations on small integers or real numbers. So I discussed the advantages and disadvantages. So the natural question is that whether there exists an efficient conversion from one to the other. So from ring LWE to LWE, the answer is relatively simple. So if you have a ring LWE ciphertext, you can simply interpret it as a bunch of LWE ciphertext without any modifications. So this is easy. The other direction from LWE format to ring LWE format is, however, difficult, and it is called as ring packing, which is the main focus of my presentation. So there has been already an extensive studies on this matter, including the ones in the list. So the straightforward application of ring packing is scheme switching. So we basically use scheme switching if we have different types of operations and different computational widths to handle. So for instance, we can imagine a complex circuit consisting of different types of operations and different computational widths. So for instance, it may include a lookup table and computations on individual beats, which is great to use LWE-based schemes. And also it may contain polynomial approximations or massive parallel computations, which it might be better to use ring LWE-based schemes. So the strategy we may use is to, for instance, start with LWE format, and if we want computations which prefers ring LWE format, then we may use ring packing, and if you want to go back to LWE format, then we convert it back to LWE and LWE and so on. So the strength of this strategy is that we can flexibly choose LWE and ring LWE based on the operations we do, and it will increase the efficiency of the strategy. The second application is transciphering, which is basically sending ring LWE-based FHE ciphertext with high granularity. Let me explain this by a typical example in homomorphic encryption. So on the left, you have a client. There is a client. On the right, there is a server. So the client wants to outsource the computation to the server. So what we typically do in ring LWE-based schemes is that first, clients have a bunch of messages, and they encrypted it to a ring LWE ciphertext and send it to the server. And in the server side, they do whatever computation they want and send it back to the client, and client decrypts it, and it's done. But the problem here is that each ciphertext sent from client to server or vice versa contain thousands of messages inside, because ring LWE contains thousands of messages, and it is too large, and it has bad granularity. So the alternative solution is to use LWE ciphertext. So at this time, the client encrypts individual messages with LWE ciphertext, send individual LWE ciphertext to clients server, and in the server side, if there are sufficiently many LWE ciphertext received, they can ring pack to ring LWE ciphertext and continue computation, and after that convert it back to LWE and so on. So by using this strategy, we can have high granularity, although we are using ring LWE-based schemes. Next, I want to describe a little details about ring LWE-based FHE schemes. First, I want to recall the notion of moduli chain. Ring LWE-based schemes are basically leveled homomorphic encryption schemes. So what I mean by leveled homomorphic encryption is that each ciphertext, there is a level assigned, and level M ciphertext is corresponded to a ciphertext modulus large QM, which is a product of small QIs from 0 to M. And when you multiply two ciphertexts with level M, then at the very end, the level decreases by 1, and the result ciphertext is at level n-1. So by using this moduli chain and level concept, I want to describe a typical life of a ring LWE-based scheme ciphertext. So on the right, you'll see the tower of moduli or tower of levels. So the black region is reserved for homomorphic computations. So typically, when you have when you want to start some computations using ring LWE-based schemes, you encrypt ciphertext to level comp, and you will lose level one by one when doing some homomorphic computations, and at last you will reach the level refresh. And the bootstrapping, it can be described as a process which sends a ciphertext at level refresh to a ciphertext at level comp. So there is another region, gray region in the tower. So they are the levels reserved for bootstrapping. This is because bootstrapping itself also consumes some levels. Next, I want to talk about encoding structure of ring LWE-based schemes. So there are slots encoding and coefficients encoding of ring LWE-based schemes ciphertext. Coefficients encoding is relatively simpler to describe. So messages are simply encoded into coefficients of the ring LWE ciphertext. And slots encoding is used to enable SIMD, I mean single instruction multiple data computation on ciphertext. So we often use DFT or NTT slots to do this, and messages are encoded in each slot. So for instance, in the CKKS scheme, there is a canonical embedding between a complex vector space C n/2 and the space of ring LW polynomials ZQX mod x2dn plus 1. And this defines the DFT slot of CKKS scheme. So I next want to describe how the encoding state changes during bootstrapping. So in the usual computation region, where between comp and refresh, every ciphertext is in slots encoded state because we want to do some SIMD functionality. But in the bootstrapping region, there are steps called coefficients to slots and slots to coefficients. Am I supposed to answer questions during the talk, or okay?
Jaehyung, you can. Usually, what we do is we let the questions accumulate in the chat, and then after you're done with your presentation, we can just stop the recording, and then we'll address the questions one by one. But
okay.
if you want to do differently, it's up to you. I mean, we can also discuss the questions. It's just that everything will be in the recording. It's up to you.
Okay, then I will handle the questions after the presentations. Thank you.
Okay, no worries. Sure.
Okay, so let me continue the presentation. So yeah, so during the bootstrapping, there are coefficients to slots and slots to coefficient steps, which converts coef encoded ciphertext into slot encoded ciphertext and vice versa. So in particular, the very first step of bootstrapping is slots to coef. So we have slots coefficients encoded state as coefficients encoded ciphertext at the very bottom and at the very top. And after you reach the top with the step called mod raise, you will perform coefficients to slots and go back to slots encoded states. In the intermediate, during the C2S or S2C procedure, the ciphertexts are literally in the intermediate between slots encoded and coefficients encoded state. So these are described in the picture. Yeah, so the brown denotes the slot encoded state, and the yellow denotes the coefficients encoded states, and the yellow only exists at the very bottom or at the very top. Now I want to define FHE ring packing. So here, here we have some different parameters to choose. So we have modulus, ring degree, and encoding structure. So for the modulus, we prefer a high modulus because we want some extra computations after ring packing. And in terms of ring degree, we also want a sufficiently high ring degree so that we can do bootstrapping. And for encoding state, we want slots encoding because it is the only state that supports CMD computation. So as a summary, our FHE ring packing is defined as follows. It is packing LWE ciphertext into slots encoded ring LWE of modulus Q comp. So this corresponds to level comp, and degree NBTS, which is any ring degree that allows bootstrapping. So we now define FHE ring packing. So I want to introduce a naive approach and its problem. So when you naively do FHE ring packing, then you will be ring packing above the modulus Q comp. And it means outputting ring LWE with large parameters. So we will be ring packing with large modulus and large ring degree. But this results in unsatisfactory runtime and key size, mainly because computation cost and the size of evaluation keys they depend on modulus and ring degree. So here, this kind of FHE ring packing strategy can be less practical. So we need some accelerations. So this is why we introduce some acceleration tools for FHE ring packing. First, we optimize the ring LWE modulus. So first, I want to recall the conventional approach, which I called naive approach in the previous section. So we will, in this method, we do ring packing above the modulus Q comp, above the level comp. But what we propose is that we first ring pack at the very bottom modulus and do some bootstrapping, some kind of bootstrapping to output ring LWE at high modulus. So here, this is not exactly the bootstrapping, but something called half BTS, which is sending coefficients encoded ring LWE ciphertext at level 0 to slot encoded ring LWE ciphertext with level comp. And to separate the ring packing at the very bottom modulus from FHE ring packing, we define base ring packing, which is defined as packing into coefficients encoded ring LWE of degree and BTS and modulus Q bottom. So the nice thing about this approach is that we perform ring packing at the bottom modulus. So the computations are accelerated and key size are decreased by greatly. So it's really great. But one thing to note is that usually this kind of optimization does not work, mainly because usually bootstrapping is the bottleneck of homomorphic computations. But in this specific case, ring packing is even more costly than bootstrapping. So we can we can take this kind of approach. We also optimize the ring degree of ring LWE ciphertext. So now we will focus on base ring packing step. We adopt the technique called ring switching. So let me briefly explain what ring switching is. When we have small modulus, then we can actually use a smaller degree ring LWE ciphertext, because basically the logarithm, base 2 logarithm of the total modulus budget is roughly proportional to the ring degree. So we first use a small degree ring LWE ciphertext, and when we have to, we can switch into ring LWE with a larger degree using key switching. So when applied to our method, we start with LWE ciphertext, but we base ring pack into smaller degree ring LWE ciphertext and ring switch to larger degree ring LWE ciphertext and proceed the computation. So the main advantage of degree optimization is that the key size is reduced by greatly, because key size is really proportional to the ring degree. So as a summary, our proposed accelerated method can be described as follows. You first have input LWE ciphertext at some small modulus. You base ring pack them to a smaller degree ring LWE ciphertext, and you ring switch to larger degree ring LWE ciphertext with coef encoded state, and you finish the process using half BTS. Now we observe what happens if we apply these to existing approaches. I want to recall that ring packing can be regarded as matrix vector multiplication. So LWE ciphertext can be described as inner product of ciphertext and secret key equals to message if we just ignore the B part of the LWE ciphertext. So if we have a bunch of LWE ciphertext, then it's a bunch of inner product equations. So this is just a matrix times secret key vector equals to message vector equation. So it is indeed a linear system with errors. And the typical way to do ring packing is we encrypt the secret key vector and homomorphically compute plain text matrix times ciphertext vector multiplication. And if we do this, then it results in ring LWE encryption of message vector, and this is the desired form. So this is the way how ring packing is regarded as matrix vector multiplication. And if you take this in mind, then existing approaches can be represented in terms of matrix times vector multiplication. So there are basically three kinds of existing methods. So column methods, row method, and diagonal method. So a column method simply reads the plaintext matrix by its columns, a row method by rows, diagonal method by diagonals. I'm not going to explain these methods in details, but I want to compare some costs of each method. So in terms of number of key switchings, column method and row method has k number of key switchings, where k is an LWE dimension of input LWE ciphertext, and diagonal method has 2 square root of key switching. So here diagonal method can be preferable. And in terms of number of keys, the column method has the largest number of keys with large k keys, and diagonal method is next with 2 square root of k keys. And finally, row method has log k keys. So at this stage, you might think that column method is kind of could be unpreferable because it is bad at a number of key switchings and number of keys. But it turns out that it is the most preferable one because it consumes 0 level during ring packing. So I will be explaining this in detail in the next slide. So I'll be comparing base ring packing with existing approaches. So there are 3 methods: column, row, and diagonal methods. And the number of levels consumed for column was 0, and the levels for row was 1, and the number of level consumed for diagonals method was more than 1, much more than 1. And actually, the number of levels consumed means that the input LWE ciphertext is at the modulus correspond to the number of levels consumed. So the more levels the method consumes, the higher the starting modulus. And also the starting modulus determines the ring degree, which we can use for ring switching. So it is even more powerful. So in terms of computation costs, it is roughly proportional to the number of levels consumed. And in terms of key size, it is roughly quadratic to the number of levels consumed. So the less modulus consumption is better. And in this regard, column method is the most effective after all the optimizations. So in the rest of the talk, I will be focusing more on column methods than other 2 methods. At last, I want to talk about our new ring packing method, HEaaN. HEaaN 0 is basically just the column method with our optimizations. So as I mentioned, it's already practically fast, but actually it has some problem. So I want to describe problems while explaining this method in detail. So as I mentioned, column method reads the plaintext matrix by its columns. So first column is multiplied by first element of the secret key vector, and second column is multiplied by second element of the secret key vector, and so on. And so we can decompose it into different products, a summation of different products. And what we do in the column method is that we regard each secret key element as a valid secret key of ring LWE system. and key switch from these secret keys to the desired secret key. So and finally we sum them all to get the desired ciphertext with message vector encrypted. But so here we need large K switching keys for this ring packing method, where K is LWE dimension. But the problem is that LWE dimension is typically large, like several thousand. So the problem of the optimized column method is that the key size is still too large. So our method Hermes1, called as a block method with our optimizations, aims to solve the problem of optimized column method, the memory issue. And so let me describe our method. So instead of reading a plain text matrix by its columns, we read them by blocks. So for this specific example, we decompose the matrix into 2x2 blocks. And so the orangish blocks are multiplied with orange block of secret key, and greenish for green. And so we can decompose it like this. And what we do is to squeeze them horizontally, as we did in the column method. So for instance, we squeeze light orange block and light green block into light gray block. And so at the intermediate step, we have a smaller matrix, which is horizontally squeezed. And after that, we read this new matrix by columns and do the analog of the column method and finishes the ring packing. So here, the nice thing about our method is that we can actually reuse the secret key blocks. So for instance, the orange secret key block corresponds to both light orange and dark orange blocks in the matrices. So we can reuse these switching keys. So to be precise, we need square root of k switching keys for the first step, and square root of k switching keys for the second step, where k is also LWE dimension. So we now have two square root of k switching keys in total. The cost of so I want to describe the cost analysis of our block method compared to the column method. So in terms of computational cost, it increased from k to k plus square root of k. So it is not so large. But in terms of key size, the key size decreases, the number of keys decreases from large K to 2 square root of K's, 2 square root K, so it's significant. So at this point, one might wonder about the details of the method. So one might wonder how to encode the blocks. So we basically use module LWE, which is a module variant of learning with error problems. So in the very first setting, we had a bunch of LWE systems. So they were just A vector A times secret key vector inner product. But in the intermediate step, the matrix is actually encrypted with module LWE encryption. So in this particular example, they have degree 2 and rank 2 module LWE ciphertext. And one might also wonder how to squeeze the blocks. So we use methods called MLWE key switching and MLWE ring switching, which is a proper adaptation of ring LWE key switching and ring LWE ring switching, respectively. If you are interested in details, you can check them in our paper. Finally, I want to briefly describe some experimental results. So first, I want to compare our results with state-of-the-art FHE ring packing methods. So the only FHE ring packing implementations in among the prior works was Pegasus, which is basically a diagonal method. So we compare with Pegasus, but I listed three different columns, three different rows for our implementations, namely optimized row method, optimized column method, and optimized block method. So optimized block method is of course Hermes 1. In this table, I first want to point out the comparison between Pegasus and Hermes 1. So Pegasus basically used a modulus Q comp of 270 beats. So we constructed a parameter with Q comp 270 beats and compared the ring packing throughput. So in the amortized time was so in terms of amortized time, our method was approximately 40 times faster than Pegasus. Note that we actually use a smaller ring degree because we were able to optimize a little bit more. And also note that Pegasus only provided implementation up to 2 to the 12 input LWE ciphertext. So it's also a little bit different. The second thing I want to point out in this table is the comparison between column method and the block method. So the main purpose of our method was to decrease the key size. So, and this is actually checked with the experiments. So the base rigging packing key size of the column method was 114 megabytes, and it was 6 megabytes for the block method. And so we could reduce the key size significantly while maintaining the throughput approximately similar. But actually still half BTS key size or bootstrapping key size is dominant in this ring packing scenario. But I want to add that the base ring packing key size of column method is non-negligible compared to bootstrapping key size, but ours is somewhat negligible. I also want to talk a little bit about some example application in CKKS in like developer's perspective. So I want to introduce the expected cost. So a typical application of Hermes would be to use it as following. So we first start with CKK ciphertext at level refresh. We first compute slow to coif to get to coif encoded ciphertext. And once you get to coif encoded ciphertext, you can do whatever LWE operations you want. And after that, you will be base ring packing or use base Hermes to ring pack and ring switch and half BTS to get to the desired output. And the So in terms of, so when we write the cost of each operation in terms of the cost of float to coif, then half BTS is approximately 9 and base Hermes is approximately 5. So base Hermes is basically, base Hermes basically costs half of the whole bootstrapping process. So for instance, if you want to do reordering using the Hermes result, then the total cost will be 15, which is 1.5 times the bootstrapping cost. Before I wrap up, I want to explain our transciphering results as well. So I want to briefly describe our transciphering strategy. So we have input LWE or module LWE ciphertext. So we encrypt real numbers with some scaling factors rather than encrypting bits. We use XOF on a public seed, and this makes the A part almost negligible. And we also cut least significant bits of the B part during transmissions to decrease the expansion ratio. So how to do our transciphering? We will be outputting slot encoding the CKK ciphertext as usual, but this time we may start with a module LWE ciphertext rather than LWE ciphertext. But this can be similarly done with our Hermes, and we will be choosing midpoint at the very middle and use the usual block method. So this is the experimental results, which is a comparison to the state-of-the-art transciphering methods. So in the table, you'll see the column named granularity. So granularity refers to the number of symmetric ciphers transmitted simultaneously during transmission step. So when we fix the granularity to be 16, then you can observe that our method is 3 to 5 times faster than the state-of-the-art while maintaining similar expansion ratio and precision. So to wrap up, we optimized the existing ring packing methods for FHE ring packing. We proposed a new efficient FHE ring packing method called Hermes, which is 40 times faster in terms of throughput compared to state-of-the-art. And we also discussed application to transciphering. Thank you for listening to my presentation.